The scariest things in the universe aren't the ones you can see coming. They're the ones where the warning and the destruction arrive at the same time. September 1st, 1859. A white light flare erupts from the sun so bright that astronomer Richard Carrington can see it with his naked eye through a telescope filter. He sketches it. He doesn't know he's documenting a gun being fired. 17 hours later, a trip that normally takes 3 or 4 days, the coronal mass ejection slams into Earth's magnetic field. It moved that fast because a prior eruption had swept the solar wind out of the way like a snowplow clearing the highway. What followed was the closest thing to an electromagnetic apocalypse the modern world has ever seen. Telegraph operators got shocked at their desks. Machines caught fire. And here's the part that still unsettles engineers. Operators disconnected their batteries, and the telegraphs kept working, powered by currents the storm induced in the wires themselves. The machines were possessed by the sun. Gold miners in the Rocky Mountains rolled out of their tents and started making breakfast because the auroras were so bright they genuinely thought it was morning. That was 1859. The world ran on steam and copper wire. Now run it again with 7,000 satellites in orbit, with GPS, with the power grid that keeps your hospital ventilators breathing. July 23rd, 2012. A coronal mass ejection of the same class as the Carrington event rips off the sun. Same speed. Same power. Earth's orbital position was 9 days ahead of the blast. 9 days. That's how close you came to losing the 21st century while Barack Obama was president, and almost nobody heard about it. But here's what actually keeps solar physicists quiet at conferences. Carved into tree rings, in Japanese cedars, in ancient bristlecone pines, are the fingerprints of something worse. They're called Miyake events. The one in 774 CE was 10 times stronger than Carrington. Another, 14,300 years ago, was stronger still. They happen roughly every 400 to 2,400 years, and right now your entire warning system is one satellite called DS-COVR parked at the L1 Lagrange point a million miles away, giving you somewhere between 15 and 45 minutes notice. This isn't a what if, this is a when. And the last time it almost happened, you didn't even know. You're probably thinking the next threat is Betelgeuse. Everyone thinks it's Betelgeuse. That bloated red shoulder of Orion, 650 light years away, wobbling toward death. And it would be spectacular, bright as the full moon, visible in daylight, enough light at midnight to read a book by. You'd step outside, and for a few weeks the sky would have two suns. But Betelgeuse can't hurt you. Not from that distance. It's a spectacle, not a weapon. The real danger comes from stars you've never heard of and couldn't see if you tried. Type 1, a supernovae. White dwarfs, dense, dim, the corpses of average stars, silently pulling matter from a companion until they hit a critical mass and detonate. No centuries of warning like a bloating red supergiant. No dimming, no wobbling, just a binary system you weren't monitoring. And then a flash brighter than a billion suns. Within 26 light years, that flash shreds half your ozone layer. Ultraviolet radiation pours through. Crop failures, ecosystem collapse, cancer rates beyond anything in human medicine. And we know this has happened nearby before. Iron-60 isotopes, an element that doesn't form naturally on Earth, are embedded in deep ocean sediments from 2.5 million years ago. A supernova, roughly 300 light years away. Fresh iron-60 has been found in Antarctic snow less than 20 years old. The debris is still raining on you. There's a supernova remnant cataloged as RxJ085-2.0-4-622. It exploded recently, possibly just 800 years ago, possibly only 650 light years away. There is zero historical record of anyone seeing it. 12 candidate systems sit within 300 parsecs of Earth right now. The supernova everyone's watching is harmless. The dangerous ones are the ones nobody's tracking. Now take everything a supernova can do and compress it into a beam. Gamma-ray bursts don't radiate in all directions. They focus their energy into tight jets, like a rifle instead of a grenade. That focusing is what makes them lethal across 10,000 light years, roughly a tenth of the entire galaxy. Two things create them: neutron star mergers where two dead stars spiral together and collide, and Wolf-Rayet hypernovae, where the most massive stars in existence tear themselves apart. There's a star called WR104. It was once called the most dangerous star in the sky. Its rotational axis is probably tilted 30 to 40 degrees away from Earth. Probably. That word is doing a lot of work in that sentence. A gamma ray burst arrives at the speed of light. There is no warning because the warning is the thing itself. Your satellites go haywire first. Then the ozone layer doesn't just thin. It's chemically destroyed in hours. The sky turns brown from nitrogen dioxide. Every GRB we have ever detected came from another galaxy. But the statistical models say there's a 50% chance one already caused a mass extinction here. The end Ordovician, 440 million years ago, when 60% of all marine life vanished. One more thing, neutron star mergers are where your gold and platinum come from. Your wedding ring was forged in the same type of event that could sterilize the planet, which brings us to something that already happened. December 27th, 2004. Most people remember that date for the Indian Ocean tsunami. But 20 hours before those waves hit, something struck Earth from the opposite direction, from across the galaxy. And almost nobody noticed. A magnetar designated SGR 1806-20, 50,000 light-years away, suffered a starquake. Its crust shifted by 1 centimeter. That sounds like nothing until you understand that this crust is at nuclear density. A sugar cube-sized piece weighs 1 billion tons. 1 centimeter of movement at that density released more energy in 1/10 of a second than the sun produces in 150,000 years. The blast, a magnitude 32 on the earthquake scale, which is logarithmic, meaning the strongest quake ever recorded on Earth, a 9, is a rounding error by comparison. Crossed 50,000 light-years of space and still had enough left to overload satellite instruments, ionize Earth's upper atmosphere, compress the magnetosphere, and bounce detectable gamma rays off the moon. Arctic fishermen reported a sudden unexplained aurora. Victoria Caspi, one of the world's leading magnetar researchers, put it plainly. Magnetars are the only deep space objects that have ever directly, physically affected Earth. Not theoretically, not in models, in data, in broken instruments. If that same burst had come from 10 light-years away instead of 50,000, it would have destroyed the ozone layer and delivered the equivalent of a 12-kiloton nuclear detonation at high altitude. The nearest known magnetar sits about 9,000 light-years out. But SGR 0501 plus 4516 wasn't discovered until 2009, when it suddenly flared. Before that, it was just dark. Invisible. This isn't a simulation. The question isn't whether a magnetar can reach you. It already did. The question is whether a closer one is hiding. Now imagine something arrives with no light at all. There may be more rogue planets drifting through the Milky Way than there are stars. Billions, possibly trillions, ejected from their solar systems during the violent years of formation. NASA's Roman Space Telescope, launching around 2027, is designed partly to count them. Your own solar system probably threw one out. Uranus is tipped completely on its side. Neptune's orbit is off-kilter. These are scars from a sibling that didn't make it. In 2024, a study by Ed Belbruno showed that the Sun can actually capture rogue planets at Lagrange points, gravitational sweet spots, and trap them in fractal orbits shaped like the Mandelbrot set. They come in, and they can't get out. Another study from the same year found that statistically, a captured rogue might already be out there in the dark edges of our system. But the real scenario isn't collision. If a rogue planet passed through the solar system, the most likely outcome is that its gravity flings Earth out of orbit entirely. Not a bang, a shove. You'd feel nothing at first. Then the sun would start getting smaller. Michael Zemkov put it simply. We would likely all freeze or possibly cook in a matter of weeks, and some of those rogue worlds might not be dead. Geothermal heat could sustain oceans under miles of ice, in permanent total darkness. Life that never once saw a star. The solar system isn't a finished product, it's a survivor of its own violent childhood. And it's still exposed. Speaking of invisible, there are roughly 100 million black holes wandering the Milky Way right now. In 2022, Hubble confirmed the first detection of an isolated stellar mass black hole, about 7 solar masses, 5,000 light-years away, found because its gravity bent the light of a background star over 300 days. That technique, astrometric microlensing, was predicted by Einstein in 1916. It took a century to actually use it. Here's what the statistics say. The nearest isolated black hole to Earth may be around 80 light-years away. For reference, Proxima Centauri, the nearest star, is 4.2. In 2024, the Gaia mission found one called Gaia BH3, 33 solar masses, the most massive stellar mass black hole confirmed in our galaxy. You wouldn't get sucked in. That's movie logic. A black hole of 10 solar masses has an event horizon only 30 kilometers across. City-sized. What it actually does is worse in a way. It's gravitational chaos over centuries. Comets start arriving from directions they shouldn't. Outer planets wobble. Orbits that have been stable for 4 billion years start drifting. And by the time you trace the cause, you've been living inside the disruption for generations. They're not rare. They're everywhere. You just can't see them. So far, everything on this list has been a thing. A star, a planet, a black hole. Something with an address even if you don't know it yet. This next one doesn't have an address. It doesn't have a location. It's a property of the universe itself. The Higgs field, the thing that gives particles mass, might not be in its lowest energy state. Think of a ball resting in a dip on a mountainside. It looks stable. It's not rolling. But there's a deeper valley below, and if the ball ever finds its way over the ridge, it falls forever. Sidney Coleman described what happens next back in the 1970s, and nobody has improved on his wording since. Vacuum decay, he said, is the ultimate ecological catastrophe. Not only is life as we know it impossible, so is chemistry. A region of space quantum tunnels to the true vacuum and starts expanding at the speed of light. Not near the speed. At the speed, the bubble edge is information itself. You cannot be warned because the warning and the annihilation are the same thing. There is no experience of dying. Your atoms don't vaporize because vaporization requires physics, and the physics just stopped. You don't feel it. You don't not feel it. There's no you for there to be a feeling. One frame you exist. There's no next frame. The good news, if it helps you sleep, spinning black holes may actually stabilize the false vacuum. And the timescale is, in the words of Arthur Hertier at King's College London, longer than the age of the universe, much longer. Tegmark and Bostrom calculated the total probability of cosmic vacuum collapse at less than 1 in a billion per year. This is the only entry on this list where there is literally nothing to do. Not prepare, not deflect, not even panic. Which makes the next one so much worse. Because this one we could do something about. NASA's Kelly Fast said it plainly in 2026. There are roughly 25,000 asteroids larger than 140 meters in near-Earth orbits, and we've only found about 40% of them. February 15, 2013. A 20-meter rock, the size of a house, enters the atmosphere over Chelyabinsk, Russia, at 19 kilometers per second. 500 kilotons. 30 times Hiroshima. 1,500 people injured. Nobody saw it coming because it approached from the direction of the sun. The entire detection network was looking the wrong way. April 13th, 2029. A Friday the 13th. An asteroid named Apophis, 370 meters wide, passes closer to Earth than your television satellites. You'll be able to see it with your naked eye from Europe, Africa, and Asia, a point of light drifting through the stars. A 2024 study found that a rock, just 0.6 meters across, impacting Apophis at the right time, could nudge it onto a collision course for a future pass. Then there was 2024 YR4, first asteroid ever to reach level 3 on the Torino Impact Hazard Scale, first to trigger a formal international notification from the Asteroid Warning Network. It peaked at a 3.1% chance of hitting Earth before being cleared. JWST is still tracking it, There's a 4% chance it hits the moon instead. And the one tool we proved actually works: DART. In 2022, NASA slammed a spacecraft into an asteroid and changed its orbit. Proof of concept. Humanity's first real planetary defense test. And it worked. There is currently no DART-class spacecraft in existence. NEO Surveyor, the space telescope designed to find the dark asteroids hiding in the sun's glare, the ones like Chelyabinsk, costs $1.6 billion. It was nearly killed by 2025 budget cuts. Congress saved it in January 2026. We proved we could push an asteroid. Then, we didn't build another pusher. The threats aren't only ahead of us. Some have already passed through. 70,000 years ago, when your ancestors were painting on cave walls, a red dwarf binary called Schultz's star flew through the outer Oort cloud at 50,000 astronomical units. It came closer to the sun than any known star in human history. The next one is already on approach. Gliese 710 arrives in 1.3 million years, plowing through the Oort cloud at 14.5 kilometers per second, stirring up trillions of icy bodies and sending comet showers into the inner solar system for millions of years after. Stellar flybys within 0.8 light-years happen roughly once every 100,000 years. There's about a 1% chance per billion years of a star passing within 100 astronomical units, close enough to catastrophically scramble the inner planets. The Oort cloud itself stretches possibly halfway to the nearest star, and out there the sun's gravity is 2.5 billion times weaker than it is at Earth. Everything is barely held. A nudge sends things falling inward. But individual stars aren't even the biggest concern. Molecular clouds, vast structures containing thousands of solar masses, sweep through our galactic neighborhood roughly every 30 million years. And the Sagittarius dwarf galaxy has crashed through the Milky Way's disk multiple times. One pass, 5.7 billion years ago, may have triggered the compression wave that formed our sun. You weren't born in safety. You were born from a collision. And the biggest collision is still coming. Maybe. Andromeda. 2.5 million light-years away, approaching at 110 kilometers per second, set to merge with the Milky Way in about 4.5 billion years. You've seen the simulations. Two great spirals tearing each other apart. It's the most famous cosmic doomsday there is. Except a 2025 study by Til Sawala changed the math. When you factor in the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, using new data from Gaia and Hubble that didn't exist before, the chance of Andromeda actually colliding drops to roughly 50-50 over the next 10 billion years. The most famous inevitable event in astronomy might not even happen. And if it does, stars don't collide. Space is too empty. Think of it as two swarms of gnats passing through each other. Your solar system has about a 50% chance of being flung 3 times farther from the galactic center and a 12% chance of being ejected entirely, hurled into intergalactic space. But none of it matters for you. The sun swells into a red giant and sterilizes Earth long before Andromeda arrives. Sawala himself said it. The end of the sun is far worse for our planet than any galaxy merger. The collision everyone fears is the least dangerous thing on this list. The universe has already fired warning shots. You've found the bullet holes. In deep ocean sediment, in Antarctic snow, in the data from satellites that buckled under a magnetar's tantrum from 50,000 light-years away. The question was never whether the cosmos is dangerous. The question is whether you'll be paying attention the next time it aims.